Now let's look a little bit more at the chemistry of amino acids. And I'm going to refer to a couple of amino acids in particular that are relevant to MSG and aspartame. Okay, so let's start off with glutamic acid. Okay, glutamic acid is an amino acid, and this particular amino acid, we have the same amino part and the acid part. Okay, the only difference, remember, was that R group. Okay, now for glutamic acid, the R group has two carbons and then a carbon with another acid group on there. Okay, so this is glutamic acid. Okay, now there's something important to realize, and that is that all of these, there's a total of 4 hydrogens in this molecule that are readily accessible. There's other hydrogens in there that I haven't drawn because they're implied, but there's 4 of them that are readily accessible. In fact, really only 3. Okay, if I were to remove one of those hydrogens, that other one would be very tightly bound and it would not be accessible. Okay, but these are acids, okay, or acid groups. And what an acid is, as you may recall, is a proton or hydrogen ion donor. Okay, that's the definition of an acid, a proton donor, right? A base, on the other hand, is a proton acceptor. All right, this is the Bronsted-Lowry definition of an acid and a base, and it works quite well. Okay, so these are acid functional groups, which means they are donors of that hydrogen ion. That means those hydrogen ions are fairly easily removed. Okay, now over here, this amino group, on the other hand, is actually a base. Amines are basic, and that means it's a proton acceptor, or a hydrogen ion acceptor. So here we're giving up a hydrogen ion, here we're accepting a hydrogen ion. And in fact, what we see is that with glutamic acid or any of the amino acids, really the way that they appear is not in this form, where we have the acid group with its hydrogen and the basic group with only 2 there, NH2. What we have is this gives up its proton and that one receives it. Okay, so in reality what we have is the glutamic acid. Let me just write it down here. I'll rewrite this. It actually receives a proton at that nitrogen, okay, giving us a positive charge over there. And on this side, the hydrogen is gone, and so we have a negative charge on that oxygen. Now remember, this is the case for any amino acid. Not all amino acids have this other acid group. Just a few of them have another acid group. Glutamic acid is one such. Okay, so whatever I have down here, that part will remain the same. Okay, so this is the form that we find glutamic acid actually present. All the amino acids in their typical form, this is how they are. They have both a positive and a negative ion in the same molecule. Have a special name for that. It's called a zwitterion, but nevertheless, this is its typical form. But it's not its only form. Okay, there's actually 4 different possibilities for the form of glutamic acid. 3 for any amino acid. There's 3 different forms that we can write any amino acid, and I'll go ahead and draw them out for you here. Okay, so one form would be, one form would be if I have that proton, an extra proton, whoops, let's see, okay, alright, so if I have a positive ion and then I give an extra proton to, let me get this in the screen here, sorry, so that nitrogen wasn't supposed to be there, but here the only difference is I've put a proton on. Okay, so it has an extra proton, and that would come from an acidic, if it's in an acidic environment, that acid would give it that extra proton. Okay, so here is our glutamic acid, but we give it a slightly different name. It's glutamic acid, and then we would say hydrochloride, okay, or glutamic acid HCl. All right. Now, no isolated substance will ever have a net charge, so this positive charge has to be balanced out by something. Normally we have this positive and negative charge. Here we replaced that negative charge. We added on a hydrogen ion, which has its own positive, so it neutralized that negative. We have to have something else to counterbalance that positive charge, and typically that would be the chloride. Okay, so there's our hydrogen or hydrochloride, and then the Cl minus would just be kind of a counter ion, most often not included in the formula. Okay, but just to balance out the charge. Okay, this is in acid conditions. All right, but if we are not in such acidic conditions, all right, we won't have that, and we'll just have the normal form like I showed a bit earlier, where we have the positive and the negative ions there. Okay, so this would be your standard glutamic acid. Okay. There's another form where we can, since this is an acid, here we have this acid functional group, a second one. All the amino acids have this acid group, but glutamic acid in particular has this other acid group. This can also give up a proton if the conditions are right, and we'll have something that looks like this. Okay, we have our NH3 with the positive charge, and then the O negative, and then over here we have another O negative. Okay, So let's look at the charges here. Here we have a positive charge, and so it has to be counterbalanced with the negative ion. This one has a 0 charge, so it's fine. It doesn't need any counter ions. This one has a positive and a negative, but then it has a negative in addition to that. So this one has a negative or a -1 charge. Okay, that means it also needs a counterbalance ion. Okay, to counterbalance the charge, and that would be typically provided by a sodium ion. Okay, now the way we name these is the acid. If you remember from your general chemistry, the acid, if you have an ATE ending on your ion and you make that an acid, it becomes ic acid. So we see the same sort of naming convention here. Looking at the other way, removing that hydrogen, here's our ATE ion, and so this is what we would call glutamate. All right, and then the sodium ion is indicated by the monosodium. Okay, because there's one sodium ion and one glutamate. So monosodium glutamate is really the same thing as glutamic acid, just under different conditions. That's the only difference. Okay, talk about that more in just a second. There's one other form, and that is if I give up a hydrogen from that basic group over there. Okay, and so that form would be if I have, it'd just be an NH2, give up that positive charge, and it would look like this. Okay, so if you're ever wondering, is there, why did we specify monosodium? Well, it's because here, what's the charge, right? It's a -2, all right? So I'd have to have 2 ions to counterbalance this form. Okay, so that would be, I'll just write it as 2Na plus, running out of space here on my paper, but this would be disodium glutamate. Okay, that's the way we would name this one. Okay, or you could have, say, calcium glutamate or something that would have the same charge balance. All right. Now, the only difference between these 4 different forms is pH. pH is a measure of how acidic your conditions are. Okay. So, if I'm in acidic conditions, the more acidic I am, the more toward the left, the way I've drawn this, it's going to be. All right, so and the actual values here, we have at this transition, okay, we have 3 different transitions here. At this transition, it's at a pH of about, depending on what source you look, it's going to be about 2.10. Okay, somewhere in that range, 2.10, 16, 19. I've seen all of those, but somewhere in that range. Okay, the pH transition here is about 4.25, and here considerably higher at 9.67. All right, so what this means is, if I take glutamic acid, the amino acid glutamic acid, and I put it under very acidic conditions, anything less than a pH of 2.10, right? Then what's going to happen is it'll turn into this glutamic acid hydrochloride or hydrogen chloride form, okay, where I protonate this oxygen and have the chloride as a counterbalance. All right. But if I increase the pH to above 4.25 but less than 9.67, then what I have is this glutamate form, okay? And assuming I have sodium as my counterbalance, it would be monosodium glutamate. Now, if I increase the pH even further, then I would have this form, the disodium glutamate, okay? So that's the only thing that is different between these different forms, okay? So